What you're watching is a SO-ARM 101 executing a three-step sequential manipulation task entirely autonomously, powered by the X-VLA Foundation model. The task sequence is: open the drawer, pick up the pincushion, and place it in the cup. This represents a significant leap from our previous single-step pick and place work. Let's talk architecture. X-VLA is an 879 million parameter vision-language-action model pre-trained on 290,000 episodes across 7 different robot platforms. For this fine-tuning run, we trained 311 million parameters, the policy transformer and soft prompts, while keeping the vision and language encoders frozen. Our camera setup uses just two views, an overhead scene camera and a wrist-mounted gripper camera, both running at 640 by 480 at 30 frames per second with MJPG compression. We found this dual camera configuration actually outperforms our earlier 3-camera attempts. The wrist camera proves essential for precise gripper positioning. The training data consisted of 75 teleoperated demonstrations, each around 25 seconds. Here's where X-VLA shines compared to ACT. We trained for just 9,000 steps. That's roughly 90 minutes on an NVIDIA L4 Cloud GPU. Compare that to ACT, which required 100,000 steps over 10 to 12 hours for a simpler single-step task on a GTX 1070. The foundation model's pre-training dramatically accelerates convergence. Key training parameters: we increased chunk size to 48, up from 32 for simpler tasks. This expanded temporal window captures the longer action sequences required for the drawer to pick to place flow. Batch size of 8 worked well on the 24 gigabyte L4. Final training loss settled at 0.071. We're testing generalization. The pincushion position varies from the training distribution. Notice how the robot adapts its approach trajectory. This is where X-VLA's foundation model pre-training pays off. ACT struggles significantly with position variations outside its training sweet spot. In formal testing, we achieved 80% success. 4 out of 5 episodes with deliberate object and position variation. When the setup matches training conditions closely, success approaches 100%. What fails? Significantly different objects cause problems. The model generalizes within its training distribution, not beyond it. And if the drawer gap is too small, the robot needs manual intervention. The total cloud compute cost for this production quality 3-step manipulation model, about $1.20. That's the power of foundation model fine-tuning. Dramatically reduced training time, better generalization, and minimal cost. This validates the X-VLA approach for complex sequential manipulation on consumer hardware. The SO-ARM 101 with a GTX 1070 can run inference locally. Cloud resources are only needed for training.